Hello everyone, welcome to the challenge question walkthrough for Edexcel's Pure Year 1 textbook, chapter 14. Okay, our first question from exercise 14a asks us to sketch the graph of y equals 2 to the power of x minus 2 plus 5 and to give the coordinates of the point where the graph crosses the y-axis. So we can think about this graph as a transformation of the graph y equals 2 to the power of x, which is a much easier graph to draw. That looks something like this, where we have the x-axis as an asymptote, and the y-intercept is going to be 2 to the power of 0, so that is just 1. Okay, now to get from y equals 2 to the power of x to y equals 2 to the power of x minus 2 plus 5, then we need to translate the graph 2 to the right and 5 upwards. And if we do the translation, so our asymptote is going to move up from the x-axis to the line y equals 5. And the graph is going to look something like this, where we've translated everything 2 to the right. And to find the new y-intercept here, we're going to set x equal to 0 again. So here we have y equals 2 to the power of minus 2 plus 5, which is equal to 21 quarters. Okay, our next question is from exercise 14e. By writing log base a of x equals m and log base a of y is equal to n, prove that log base a of x minus log base a of y is equal to log base a of x divided by y. So, if we think about using our log definitions here, if we have log base a of x is equal to m, that means that x is equal to a to the power of m. And doing the same for log base a of y being equal to n, we have that y is equal to a to the power of n. So if we now think about what x over y is, then we'll have a to the power of m over a to the power of n, which is equal to a to the power of m minus n. So we have that x over y is equal to a to the power of m minus n, and if we take log base a of both sides, then we have log base a of x over y is equal to log base a of a to the power of m minus n. Now on the right hand side here, we'll have the log base a and the base of a there cancelling, so we're just left with m minus n, and we know that m minus n is going to be equal to log base a of x minus log base a of y. So we've shown that log base a of x over y is equal to log base a of x minus log base a of y as required. Our next question is from exercise 14g. The graph of the function g of x equals a e to the power of bx plus c passes through the points 0, 5 and 6, 10. Given that the line y equals 2 is an asymptote to the graph, show that b equals 1/6 times ln of 8/3. Okay, to start with, we know that the line y equals 2 is an asymptote to the graph, and we know that any function of the form y equals a e to the power of bx is going to have an asymptote at the x-axis. It will look something like this. So we know that the curve y equals a e to the power of bx plus c is going to have an asymptote at the line y equals c. Okay, so we know that c must be equal to 2. So we have g of x equals a e to the power of bx plus 2. And now we've got 2 points we can use to find the values of a and b. So first of all, if we use 0, 5, then we have 5 is equal to a e to the power of 0 plus 2. And e to the power of 0 is just 1. So we have that a must be equal to 3. Now if we do the same for the point 6, 10, then we've got 10 is equal to 3 times e to the power of 6b plus 2. So e to the power of 6b is going to be equal to 8/3. And therefore, taking ln of both sides, we have 6b is equal to ln of 8/3. So b is equal to 1/6 ln of 8/3 as required. Okay, our next question comes from exercise 14H. Find the formula to describe the relationship between the data in this table. So, because we're in chapter 14, we can assume that the formula is either going to be of the form y equals ab to the power of x, or y equals a x to the power b. Now we can clearly see that x and y don't have a linear relationship. Now for these two equations, if we take logs of both sides, then for our first one, we're going to have log of y is equal to log of a b to the power of x, and using our laws of logs, and we can split this up into log of a plus log of b to the power of x, and using the power rule, we can bring the x down to the front. So log of y is equal to log of a plus x times log of b. And for our second equation, taking logs of both sides, and using the laws of logs again, on the right hand side, we get log of a plus b log of x. So we can see that we're either comparing log of y with x, or log of y and log of x. Now we can construct a table to compare x and log of y for the values 1, 2, 3, and 4. And we can do the same for log of x and log of y. Just using your calculator to find these values, you should get for the top table 0.72, 0.67, 0.63, and 0.58. And for the second table, we're going to get 0, 0.30, 0.48, 0.60 on top. And then on bottom, we're going to have 0.72, 0.67, 0.63, and 0.58 as above. Okay, so now all we need to do is have a look at which one seems to be linear. But you'll see that if you plot the points for this first table here and join, you get a linear relationship. So we know that our line must be of the form log y is equal to log a plus x log b. And from your sketch, you can estimate values of a gradient and the y-intercept. And the gradient turns out to be about minus 0.045, and the y-intercept about 0.76. Now if we compare the value of the gradient and the y-intercept to our equation here, then we have the gradient minus 0.045 is equal to here, this log b. So log of b is equal to minus 0.045, and then the log of a is our y-intercept, so that's going to be equal to the 0.76. Now to cancel out the logs on the left-hand sides of the equations here, we can raise them as a power of 10. So here we're going to have b is equal to 10 to the power of minus 0.045, which is about 0.90. And then for the second equation, we're going to have a is equal to 10 to the power of 0.76, which is equal to 5.75. And so our formula is going to be y is equal to 5.75 times b, which is 0.90, to the power of x. And that is our formula as required. And our final question is for mixed exercise 14. Part A says, given that y equals 9 to the power of x, show that log base 3 of y is equal to 2x. So we can rewrite 9 to the power of x as 3 squared to the power of x. So we have y equals 3 to the power of 2x. Now, if we take log base 3 of both sides, then we're going to have log base 3 of y is equal to log base 3 of 3 to the power of 2x, which is just 2x as required. And part B says, hence deduce that log base 3 of y is equal to log base 9 of y squared. So we have that y equals 9 to the power of x. So if we take log base 9 of both sides, then we have log base 9 of y is equal to x. We also know that log base 3 of y is equal to 2x. So 2 log base 9 of y. So we have log base 3 of y is equal to log base 9 of y squared using the power rule as required. And finally, part C says use your answer to part B to solve the equation log base 3 of 2 minus 3x is equal to log base 9 of 6x squared minus 19x plus 2. So we have y is equal to 2 minus 3x and y squared is equal to our 6x squared minus 19x plus 2. And if we call this equation 1 and this equation 2, then we can substitute equation 1 into equation 2. So we have 2 minus 3x all squared is equal to 6x squared minus 19x plus 2. So we have 4 minus 12x plus 9x squared is equal to 6x squared minus 19x plus 2. And moving all the terms to the left-hand side, we have 3x squared plus 7x plus 2 is equal to 0. And if we factorize here, we're going to have 3x plus 1 and x plus 2 is equal to 0. So our two solutions are x equals minus a third and x equals minus 2. And finally, we just have to check that our solutions actually do work in the first equation, because remember we can't take logs of a negative number. So if we plug in x equals minus a third into 2 minus 3x and 6x squared minus 19x plus 2, then it's all positive, so we're fine. And doing the same for x equals minus 2, they're all positive again. So these are both valid. Solutions to our original equation. And that is the end of the challenge questions for chapter 14. I hope you enjoyed this video, and I'll see you next time.